Electricity can be generated using a water turbine. Water gains kinetic energy by falling from the top of a dam. Calculate the minimum height that 7 kilograms of water must fall to gain 1,300 joules of kinetic energy. So we've got height, we've got mass, and we've got energy, kinetic energy, and possibly which can be linked to gravitational potential energy. So we're trying to work out height. So height is a distance, and this is a suitable formula you can use. There's actually two formulas you could use, but let's focus on this one first. Work done is basically another word for energy used, so energy transferred. So work done is measured in joules, so that would account for this. Force and distance. So force is the effect of gravity on a mass, and we've got mass. So by multiplying this by the gravitational field strength, so gravitational field strength of our planet is always 10, very easy. So by multiplying 7 by 10, we get 70 newtons, and then we have our force over here. So now we've got this, and we've got work done here. We just need to rearrange it. So work done divided by force will give you distance. If you're not sure how I did that, remember my 632 method. So just add in these numbers which make sense. So 3 times 2 would be 6. So force was 3 and distance was 2. Work done would be 6. Now these values are attached to these. We can manipulate them and rearrange it so it helps us rearrange the equation. So we want to work out distance here, and we've got 6, 3 and 2. So what would we do with these numbers to make 2? Well, 6 divided by 3 would be 2. So work done divided by force will give me distance. So finally, 1,300 joules divided by force, which is 7 times 10, which is 70, because of the gravitational field strength, will give me 19 meters to two significant figures. However, there's another way to work this out as well. Remember that before the water is released, it has maximum gravitational potential energy. And what will happen is, as it falls downhill, that will be transferred to the kinetic store in the water. So by the time it gets to the bottom, there's no energy left in its gravitational potential store, and in its kinetic store, it's at max energy. So all that GPE has been transferred to the KE store. Why that's useful is because that helps you understand that over here, it's the same value as the kinetic energy. So GPE and kinetic energy are substitutable. So we can use this formula as well. GPE equals mass times gravitational field strength times height, and we're doing pretty much the same thing. All we're doing this time is understanding that 1,300 joules is the same for GPE, because that's what it was up here. And then we do the same thing, mass times gravitational field strength. Mass is 7 kilograms times 10 newtons per kilogram, which will give us 70, and we end up with the same answer. So there's two ways to get the same answer. As water enters the turbine at the bottom of the dam, the kinetic energy of 8 kilograms of moving water is 1,100 joules. Calculate the speed of the moving water as it enters the turbine. So this time we've got energy, we've got mass, and we want to work out speed. This is now involving this equation, kinetic energy equals half mv squared, where speed is being substituted for velocity here, so how fast something's moving. So ke equals half mv squared, and we want to work out this. So again, we're going to need to rearrange. So the first thing we do is we need to divide both sides by half, because this side's been multiplied by half. Remember, we want to isolate this. We want to work out the speed. So kinetic energy is 1,100. So we divide this by half, and that will give us 2,200, and that will have the effect of cancelling this on this side. Next, this has been multiplied by mass, so to get rid of it, we need to divide by mass. So the next part is dividing by mass. So by dividing this by mass and dividing this side by mass, the effect is we get rid of mass on this side, and we end up with 2,200 divided by 8, which is 275. Now we're left with ke equals velocity squared. So we have to reverse, velocity's been squared, so to reverse it, we need to square root it. So by square rooting it on this side, we get rid of it, so we have to square root our answer here as well. And by doing that, we get 16.6 meters per second. When in doubt with this one, I know it seems very complicated, but they're just 3 simple steps. When you're trying to work out velocity from this equation, you just divide your answer, kinetic energy, by half, then divide by the mass, then square root it. That's all you do, 3 steps. If you can remember, divide by half, divide by mass, square root, you'll get velocity. Moving air can be used to generate electricity using a wind turbine. Figure 8 is a graph of kinetic energy against the wind speed for a mass of moving air. So we've got kinetic energy of moving air here and wind speed here. So you can see as there's more wind speed, or the faster the wind's traveling, the more kinetic energy of moving air there is in kilojoules. Just before the air reaches a wind turbine, it has a speed of 15 meters per second. So that's over here. I've drawn a red line here, which translates to 5.2 kilojoules of energy. When the air has gone through the turbine, it has a wind speed of 13 meters per second. So after it's gone through the turbine, so this is before and after. So if you imagine you've got this turbine here, which is traveling, and we've got air coming in here and then air here, and we can see it has more energy here. It's got 5.2 kilojoules. Oops, sorry, wrong pen. We've got 5.2 kilojoules here and 4 kilojoules here. So you can assume that some energy is being transferred out. This is partly to turn the turbine, so the kinetic energy in the turbine, but also some will be lost to the environment as heat due to friction in the mechanical parts rubbing against each other. Anyway, as the air moves through the turbine, some of its kinetic energy is transferred to the turbine to make it turn. Use the graph to determine the percentage of kinetic energy transferred to the turbine from the air. So, firstly, we've worked out how much energy the air initially had, and we're trying to work out what percentage of this is transferred into the moving turbine. So the amount that's transferred here is the difference between these two values, so 1.2 kilojoules, this take away this. So to work out percentage, you just do 1.2 divided by the total, or the initial amount. So this is the amount we're interested in, this is the amount that's making the turbine turn, but what proportion is that of the original amount of energy in the air, which is 5.2, times by 100, which is 23.1%. And that makes sense because that is roughly about a quarter of this value, or a fifth to a quarter of this value, so that makes sense. One thing I will say, notice how the scale here isn't very easy, so you can't do nice regular steps. So how to work out what each of these equals is you take the number here and you divide it by the number of squares. So you do 2 divided by 5, and that will give you 0.4. So each one of these squares is 0.4. So 0.4, 0.8, 1.2, 1.6, 2. And so you can be accurate, but I think they'll also give you a little bit of leeway if your answer is slightly out.